Hello students, welcome to another edition of CEC Gurukul lectures. Today we will be talking about closed loop operational amplifiers. If you look at our previous lectures, we had already started with operational amplifiers and the same were discussed in open loop configuration. So today we will see how closed loop operational amplifiers score over the deficiencies of open loop configuration. So before we start and compare the open loop and the closed loop configurations, we need to revise the very basic operational amplifier. As we understand and you see on the screen that the op-amp, the operational amplifier, the acronym is op-amp, it's a differential amplifier and it has two inputs and one output. It uses a dual power supply. So we understand that the op-amp is a direct coupled high gain amplifier. We had seen that it is a versatile device that can be used to amplify DC as well as AC signals. And the main function of this amplifier is to perform mathematical operations including addition, subtraction, multiplication, differentiation and integration. It is used for various applications including AC-DC signal amplification, inactive filters, oscillators, regulators and finally we will see comparators. So once again a fast revision, it is a 8-pin DIP, that is the IC has dual inline package where 2 is the inverting input, 3 the non-inverting input and 6 the output. It has power supplies, it has no connection in pin number 8 and it has power supplies in 4 and 7. 1 and 5 are the offset null pins. Again a quick recap, we understand that offset voltage arises in this op-amp because most of the contents or components inside the IC are made up with semiconductor components. So as we understand that there is always a mismatch occurring due to temperature gradient and we find that there is spurious voltage or rather offset voltage coming out of pin number 6 even when pin number 2 and pin number 3 are grounded. So pin number 1 and pin number 5 are the offset null pins. So we also discussed the ideal op-amp wherein it exhibited ideal characteristics including that it should have, the ideal op-amp should have a very high input impedance and in this case it should be infinite, a 0 output resistance or impedance depending on the signal under consideration. Then it should have infinite bandwidth, CMRR and slew rate. So when we studied the op-amp in open loop configuration, we found that it does show high input resistance, but more is required. So open loop configuration was also limited by the fact that it could not be used as an active amplifier because of the high gain, rather very high gain associated with it, which tends to take the op-amp in open loop configuration to operate only in plus and minus saturation modes. So we need to move on to what is known as the closed loop configuration, and in the closed loop configuration we will again compare the differential amplifier, the inverting amplifier and the non-inverting amplifier. So, moving forward to the closed loop configuration, we understand the closed loop typically means that there is a feedback in the amplifier from the output to the input. A part of the signal is fed back from the output to the input. Now we have to see whether that feedback has a positive form or a negative form. So, closed loop op amp simply means that one, it has a feedback circuit and other the op amp as it is. So, there can be four ways of connecting these two blocks when we have a feedback. One is a voltage series feedback, wherein the voltage is fed back, the output voltage is fed back to the input in series. We have voltage shunt feedback, wherein the voltage is fed back to the input in parallel. Current series feedback, wherein the current is fed back to the input in series, and current shunt feedback, wherein the current from the output is fed back to the input in parallel. So, the typical diagrams associated with the four kinds of feedback circuits are shown in this slide, and we can easily see that the voltage is always taken out in parallel from the output, whether it is a voltage series feedback or voltage shunt feedback, but voltage taken from the output is always in parallel. Similarly, whether it is a current series feedback or current shunt feedback, the current from the output part of the circuit is always taken in series. In input, it is a series or a shunt feedback, but always the current is taken out in series from output part of the circuit. Now, voltage shunt and voltage series are the most commonly used configurations in the op amp, and by using a feedback circuit, a part of the output signal is fed back to the input circuit. The positive feedback means that the input increases as a result of the feedback signal, because the output is fed in phase with the input signal in the op amp. The negative feedback means the feedback is 180° out of phase with respect to the input, and hence it is natural to expect that the gain of the circuit would be reduced a bit when we have a negative feedback. But as we would see that in the coming slides, that is, that the negative feedback is always preferred in amplifiers. That's because it imparts stability to the functioning of the circuit. The positive feedback is preferred whenever we have to design an oscillator. So, therefore, keeping all these points in mind, we move forward to today's discussion, that is feedback or closed loop op amp circuits. So, generally negative feedback is preferred because a small differential input is necessary to create a large signal at the output as far as op amps are concerned. This we had seen previously with open loop configurations too. So, with the drawback of the open loop configuration was that even if we sent back a very small differential input to the op amp, since the gain was very high, Therefore, the op-amp could only operate in either plus saturation or minus saturation modes. Hence, the requirement of a negative feedback, because it acts as a self-correcting facility against any change in the output voltage that may be caused due to changes in environmental conditions, including voltage fluctuation, temperature variation, and other circuit stability problems. So, moving forward, we see the first one, that is the voltage series feedback amplifier. In this case, it is pertinent to note that the op-amp here is biased in non-inverting configuration sorry, non-inverting configuration, wherein the input signal is connected with the positive terminal, that is third input of the op-amp. In open loop configuration, as we can see, the feedback was not there. So, therefore, the op-amp would simply shift to positive saturation. This presence of this feedback resistance is to provide stability to the circuit. Now, we would analyze the functioning of this circuit as to how the feedback is giving stability. It is important to note that from point number 6, which is the output connection on one end is connected to RF resistance, whereas the RF resistance is connected to the R1 resistance and input terminal number 2 at the other end. So, output voltage, that is V naught, drives a current through the RF, and from RF it comes to a junction from where the current can go to two different paths. The one path is your pin number 2 and the other path is the resistance R1. So, in the feedback circuit, it can be seen that the point or the junction from where the current has to choose a path, therein the current chooses the path through the R1. That is because the input impedance of the op-amp is very high, and therefore, the current cannot enter the op-amp through pin number 2, because the internal resistance or internal impedance, as we can see, we've seen a couple of slides before. For example, the basic op-amp, as we had seen, has a resistance between the points number 2 and point number 3, which are the two inputs. The resistance here is very high, and therefore, the amount of current going inside the op-amp is negligible. Hence, in this circuit with feedback, the current coming out of RF chooses to pass or has to pass through the resistance R1 and goes to the ground. Therefore, the current, if you look at the circuit, the current goes to the ground through the pin number R1, through the resistance R1. It is also pertinent to note that while designing the circuit, the value of RF should be greater than the resistance R1. Now, the current passing through R1 would create a voltage drop across it. And what is the total current that is flowing through this circuit? It can easily be calculated like V naught drives a current that passes through RF and then through R1 before reaching the ground. Now, this means that this circuit is a series circuit with no branching of the current. And with our discussion that was done a couple of lines back, we can understand that why current does not go to pin number 2 of the IC. Now, the total current that needs to be calculated here is V naught divided by the total resistance in the path of the current, and total resistance here is Rf plus R1. Hence, the total current is V naught divided by Rf by R1. It is also important to note that this circuit is a potential divider circuit, and Kirchhoff's voltage law states that the amount of voltage associated with any circuit is equal to sum of the independent voltages within the circuit. So, herein we would have V naught as equal to I Rf plus I R1. So, therefore, the voltage V naught would be equal to V Rf and V R1. So, if we calculate the voltage drop across R1, it would be I R1, I total R1, because this one is a series circuit starting from V naught. So, therefore, again looking into the circuit, we see that this voltage is being fed back to the pin number 2, and that way the op amp in this configuration actually amplifies the input voltage minus the feedback voltage to calculate the total amplified voltage. Now, that is equal to, as the Kirchhoff's voltage law equation is shown over in the screen, we find that total Vd, which is the differential voltage, and this notation is being continued from our previous lectures. So, Vd is equal to Vn minus Vf. So, therefore, the idea is to calculate the value of the voltage, the amplification in terms of the voltage and the resistances that are affixed with the circuit. It is these resistances which help us calculate the amount of amplification that one can derive from this circuit. So, feedback voltage, as can be seen here, always tends to oppose the input voltage, or rather in technical terminology we can say that it is 180-degree out of phase with the input voltage, and the feedback is therefore called negative. So, ACL stands for A is the voltage amplification, CL stands for closed loop. So, in this case we can see that if we substitute all the values, in this case we find that V output comes out equal to 1 by Rf by R1 times the A open loop. So, therefore, in other words, the total closed loop voltage gain offered is equal to 1 plus Rf by R1. So, hence it is readily seen that in this case the closed loop voltage is dependent directly on the values of Rf and R1 being chosen. It is important to note that the value of RF should always be more than the value of R1 in order to get a stable amplification for the circuit shown. So, right now, after this is done, we use the same circuit, that is the non-inverting op-amp circuit, in feedback mode to calculate the critical parameters associated with the circuit. The first one is the input resistance. So, what we want from this circuit is that the input resistance associated with closed loop configuration should be more than one gets with open loop configuration. Only then does moving from open loop to closed loop make sense, because for an ideal op amp one needs to have an input resistance that should actually be reaching or attaining infinite value. So, another very critical aspect to note with this circuit is that for negative feedback in non-inverting configuration, the voltage input is to be affixed with pin number 3, which is the non-inverting input. However, the feedback is to be associated with the pin number 2. The greatest mistake that as a student while designing the circuit we make in the laboratories is that we tend to fix the feedback also to pin number 3. That is to be avoided at all costs, because negative feedback gives you the stability, whereas positive feedback increases the gain, but it is a compromise with the stability of the circuit. Now, we do the necessary derivations, and our syntax is that we use Ri for the input resistance of op amp in open loop configuration, and we use R with subscript of IF as the input resistance of the amplifier with feedback. One another thing that as a student we tend to make a mistake is that we confuse Ri with R1. Many books have this printing mistake. Ri is inside the IC, R1 is the resistance we affix outside the IC. So, keeping these things in mind, we move forward and see that RIF, after substituting all the values, RIF becomes equal to Ri into 1 plus AOL beta, as we had defined earlier that AOL is typically of the value of 2 into 10 to the power 5. So, from this equation we see that RIF becomes many times larger, of the orders of tens of magnitude compared to Ri. Hence, closed loop configuration actually helps increase the input resistance. So, we will soon come back with the next analysis of the closed loop configuration. Thank you.